Welcome to Lecture 13, Network Forensics. This is your Professor T. Farid Muhammad. Network forensics is a specialized branch of digital forensics focused on monitoring, capturing, analyzing, and interpreting network traffic to detect and investigate security incidents, cyber attacks, or unauthorized activities. Unlike traditional forensics, which examines stored data, network forensics deals with dynamic data transmitted over networks, requiring tools like packet sniffers, flow analyzers, and intrusion detection systems or IDS to collect and scrutinize traffic patterns. Investigators use this data to trace attack sources, identify malware, reconstruct data breaches, and gather evidence for legal proceedings. Key challenges include handling high volumes of encrypted traffic, ensuring data integrity, and maintaining chain of custody. Effective network forensics help organizations respond to threats, comply with regulations, and strengthen cybersecurity defenses. The learning objectives and key concepts we will discuss in this lecture are explain how to perform network packet analysis. Key concepts will be network packet structure, network packet capture, network packet analysis, router forensics, and firewall log forensics. Network basics. Let's look into this with an example. IPv4, also known as Internet Protocol version 4, is the most widely used protocol for routing network traffic. Despite the growing adoption of IPv6, which I'll discuss a little later in this discussion, in a university setting, if we look at IPv4, addresses are essential for connecting various devices, including student laptops, research servers, administrative systems, and IoT-enabled campus infrastructure. Due to the limited number of available IPv4 addresses, approximately 4.3 billion actually, universities often rely on techniques like network address transmission or translation called NAT and dynamic host configuration protocol DHCP to efficiently manage address location. For example, a university may assign private IPv4 addresses like 192.168.x.x or 10.x.x.x to dormitory networks while using NAT network address translation to share a smaller pool of public IPs for internet access. However, the security of IPv4 addresses can pose challenges for large universities with thousands of devices. To optimize usage, IT departments may implement subnetting to divide networks into smaller segments, such as separate subnets for academic departments, research labs, and administrative offices, improving security and traffic management. Additionally, universities may lease or purchase additional IPv4 addresses from regional internet registries RIRS or use IPv6 in parallel to accommodate growth. Despite its limitations, IPv4 remains crucial for legacy systems and compatibility, requiring universities to balance efficient address management with future-proofing their networks. IPv6, on the other hand, Internet Protocols version 6, was introduced to overcome the limitations of IPv4, offering a vastly expanded address space with 340 undeclined unique addresses, ensuring that universities can accommodate the growing number of connected devices, from student smartphones to research lab equipment. Unlike IPv4, IPv6 eliminates the need of NAT, network address translation, allowing the true end-to-end connectivity, which is particularly beneficial for peer-to-peer research application, VoIP systems, and IoT-enabled campus infrastructure. For example, a university might assign a unique global IPv address such as 2001 db8 mt 1 to each device, simplifying network management and improving security through built-in IPsec support. Open Systems Interconnection or OSI model. It's a layer, 7 layers thing that starts with physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. Let's look into this in more detail. Hypertext transfer protocol is HTTP messages. A message can be get, head, put, post, delete, link, unlink. Whereas get request to read a web page, head is a request to read the head section of the web page, and put is a request to write a web page, where post is a request to append to the page, delete is remove the web page, link connects to existing resources, unlink is break an existing connection between two resources. Network packet analysis. Let's look into this with an example. Network packet analysis is a critical process for monitoring, troubleshooting, and securing university networks by capturing and inspecting data packets traversing the infrastructure in an academic environment. This technique helps IT teams detect anomalies such as unauthorized access attempts, malware infection, or excessive bandwidth consumption. Common issues in large networks with thousands of connected devices. For example, a university might use tools like Wireshark or Zeek, formerly known as Bro, to analyze traffic between research labs, lecture halls, and dormitories, identifying suspicious patterns like port scans or data exfiltration. Packet analysis also aids in optimizing network performance by pinpointing latency issues, misconfigured devices, or bottlenecks in high traffic areas like campus Wi-Fi networks. The network packet analysis continued. It has a payload, the body of information, content of the packet, actual content that the packet is delivering to the destination, and if packet is fixed length, a payload may be padded with blank information or specific patterns to make it right size. Beyond the security and performance, packet analysis supports compliance and the data protection regulations such as FERPA, GDPR in the university setting by ensuring sensitive student and research data is transmitted securely. Universities often deploy intrusion detection systems or IDS like Snort and or Shurikata to automate packet inspection to flag policy violations. Some important ports are port number 20, 21, 22, 23, 25, 53, 80, 110. So the best recommendation is that you should look into that. These 2021 is File Transfer Protocol or FTP, 22 is Secure Shell or SSH, 23 is Telnet, 25 is Simple Mail Transfer Protocol SMTP, 53 is Domain Name Service, and 80 is Hypertext Transfer Protocol. 110 is Post Office Protocol version 3. Important intruder ports: 407, the utility is Timbuktu, 6666 is the Beast, 23476 or 23477 is Donald Dick, and 31337 is Back Orifice, 43188 is Reach Out, and 54320 54321 is B02K. Network attacks: the denial of service, ping of death, ping flood, teardrop, and the list goes on. Let's look into the dynamic denial of service in a little bit more depth. Can be targeted at a given server, increased traffic affects rest of the target network. Attacker usually floods the network with malicious packets, preventing legitimate network traffic from passing, and the list goes on. Attacker uses the three approaches: damage the target machine's ability to operate, overflow the target machine with open connections at the same time, uses the bandwidth to target machines. Ping of death attack is in reality the attacker sends an Internet Control Message Protocol ICMP echo packet of a larger size than the target machine can accept. Firewalls can be configured to block incoming ICMP packets completely or to block ICMP packets that are malformed or of an improper length. Ping flood and teardrop. Ping flood sends a tremendous number of ICMP packets to the target, hoping to overwhelm it. Can be very effective when executed by a large number of coordinated source computers against a single target computer. Distributed denial of service or DDoS attack is also the ping flood. The teardrop attack, attacker sends fragments of packets with bad values in them, causes the target system to crash when it tries to reassemble the fragments. SYN flood attack. Attacker sends unlimited SYN technically synchronized requests to the host system. The first step in initiating communication, SYN requests are supposed to be responded to by the attacker system but are not. Attacker sends the target the starting SYN request, causing the server to set up some resources to handle the connection, and responds to the client with both the SYN and ACK, which is technically acknowledgement, bits turned on. Attacker is supposed to respond with the ACK bit turned on, which is acknowledgement, but instead just floods the target with SYN packets, never responding with ACK. Can overwhelm the target system with phantom connection requests and render it unable to respond to legitimate requests. Land attack. Attacker sends fake TCP transmission control protocol SYN packet with the same source and destination IP address and ports as the target computer. Victim computer is tricked into thinking it is sending messages to itself because the packet coming from the outside uses the computer's own IP address. Smurf attack generates a large number of ICMP echo requests from a single request acting like an amplifier. Causes a traffic jam in the target network. If the routing device on the target network accepts the requests, host on that network will reply to each echo, increasing the traffic jam. A Fraggle attack can often bypass a firewall similar to a Smurf attack, except that it uses spoofed UDP packets instead of ICMP echo replies. DHCP starvation and HTTP post attack. DHCP starvation is a cyber attack that floods a dynamic host configuration protocol server with fraudulent requests, exhausting its pool of available IP addresses and preventing legitimate devices from connecting to the network. In a university setting where thousands of students, faculty, and IoT devices rely on DHCP for automatic IP assignment, such an attack can disrupt critical operations from online lectures to research collaborations. An attacker might use tools like Yersinia or DHCPX to rapidly request leases with spoofed MAC addresses, leaving no addresses for genuine users. This can cripple campus Wi-Fi lab computers and even administrative systems if the DHCP services are overwhelmed. To mitigate DHCP starvation, universities implement safeguards such as DHCP snooping on network switches, which filters unauthorized DHCP messages and blocks rogue service. Additional measures include rate limiting DHCP requests per port and enabling port security to restrict MAC address flooding. Some institutions also use static IP reservations for critical devices such as server sprinters, while relying on DHCP for general user access. Monitoring tools like SIEM systems can detect unusual spike in DHCP traffic, triggering alerts for IT teams or to investigate by proactively rendering and hardening DHCP infrastructure. Universities ensure reliable network access while defending against denial of service or DOS attacks that target the essential services. HTTP post attack is a type of web based exploit where an attacker overwhelms a server with a flood of post requests, often a part of denial of service or brute force attack to exhaust server resources, degrade performance, or exploit vulnerabilities in web applications. In a university environment, such attack can disrupt critical services, including learning management systems such as Moodle or Canvas or Blackboard, student portals, and research databases. For example, attacker might automate thousands of form submissions to a course registration page, slowing down or crashing the system just as students attempt to enroll in the classes. More sophisticated attacks may inject malicious payloads such as SQL injection, cross site scripting, through post data, compromising sensitivity of the system and sensitive information like grades or personal records. To defend against HTTP post attacks, universities employ web application firewalls to filter and block suspicious traffic patterns such as abnormally large payloads or rapid request rates. Uh, it's also known as rate limiting and CAPTCHA challenges can also mitigate automated form submissions while input validation prevents code injection attacks. Additionally, intrusion detection systems, IDS, or log monitoring tools help IT teams detect unusual post requests, spikes, and respond before services are disrupted. Regular penetration testing and security patching of web applications further reduce vulnerabilities. By implementing these measures, universities can maintain the availability and integrity of the web based services while protecting against malicious post based exploits. Let's look into PDOS, login DOS, and packet mistreating. So PDOS is permanent denial of service attack that damages the system so badly that victim machines need to be operated and operating system reinstall or even new hardware, sometimes called flashing. Usually involves a DOS attack on the target device's firmware. Login DOS attacker overloads the login process by continually spending login requests, may enumerate usernames through another vulnerability and attempt to authenticate the site seeing valid and site using valid as well usernames and incorrect passwords, locks out accounts after specified number of failed attempts. Packet mistreating occurs when a compromised router mishandles packets, results in congestion in the part of the network. Packet mistreating also refers to the deliberate manipulation, interception, or malicious handling of network packets to disrupt communications, steal data, or bypass security measures. In a university setting where vast amounts of sensitive research data, student records, and administrative communications traverse networks, such attacks pose serious risks. Attackers may employ techniques like packet injection, inserting malicious data into a stream, packet replay, resending captured packets to exploit sessions, or packet fragmentation attacks, overwhelming systems with malformed fragments to evade detection. For example, an attacker could intercept unencrypted packets in a campus Wi Fi network, altering grades, submitting to the learning management system, or injecting malware into software downloads from university servers. To defend against packet misreading, universities implement encryption protocols such as TLS IPsec to protect data in transit, ensuring packets cannot be read or modified in flight. Network Intrusion Prevention System or NIPS and Deep Packet Inception or DPI tools monitor for abnormal packet structure or suspicious retransmissions. Additionally, strong authentication mechanism such as A22.1x for network access prevents unauthorized devices from intercepting traffic. Register vulnerability assessments and network segmentation, such as isolating research labs from general student traffic, further limit attack services. By combining these measures with continuous traffic monitoring, universities can detect and mitigate packet level exploits before they compromise critical systems or data integrity. So, network traffic analysis tool Sniffer, software or hardware that can intercept and log traffic passing over a digital network, extracts network packets, and performs statistical analysis on the dumped information. Commonly applies sniffers including TCP dump or Unix platforms and WinDump for the Windows. TCP dump a commonly applied sniffer for various Unix platforms. WinDump is a version of TCP dump for Windows. Both programs extract network packets and perform statistical analysis on dumped information. Wireshark is packet sniffer and network protocol analyzer. Analyzes real-time and saved data. Supports IPv4 and IPv6 is freely available. A Wireshark main screen looks like this. Packet details come like this. Follows transmission control protocol stream like this. Wireshark TCP sequence statistics comes for us to look at all the details of the Ethernet like this. Nmap allows the user to map out the ports are open, what ports are open on a target system, and what services are running. Let's look into this with an example. Nmap or Network Mapper is a powerful open source tool used for network discovery, security auditing, and vulnerability assessment, but it can also be weaponized by attackers to probe university networks for weaknesses. In an academic environment, Nmap helps IT teams map devices, identify open ports, and detect misconfigured services across campus infrastructure, from research labs to administrative systems. However, malicious actors may use Nmap to conduct reconnaissance before launching attacks, scanning for vulnerable web servers, outdated WordPress portals, exposed databases, or unused IoT devices such as smart classroom equipments. To mitigate Nmap-based threats, universities deploy intrusion detection prevention systems (IDS, IPS) like Snort or Suricata. It's SURICATA to flag aggressive scanning patterns such as SYN sweeps, UDP scans. Firewall rules can limit responses to probing attack packets, dropping ICMP echo requests, while port security and network segmentation reduce exposure of critical systems. Ethical hacking courses and controlled Nmap training for IT students help turn a potential attack tool into a defensive skill, teaching future professionals to audit networks responsibly. By balancing proactive scanning for vulnerabilities with robust monitoring for malicious activity, universities can harden their networks against both external attackers and insider threats. So Nmap looks like this. TCP dump, one of the most Common packet scanners for Linux, also ported to Windows, can alter TCP dumps behavior with a variety of command flags. And the command flags could be TCP dump host 192.168.2.3 will only show user traffic going to or from 192.168.2.3. TCP dump dash I any gets traffic to and from interface on your computer. ETH0 will only get traffic for the interface ETH0. Port 3389 will only show traffic for 3389. So I would suggest you to give it a try when you're working in your labs in the computer forensics. Snort and NetWitness. Let's look into this with an example. Snort is widely used open source intrusion detection and prevention system (IDPS) that plays a critical role in safeguarding university networks against cyber threats. In a campus environment where thousands of devices connected daily, ranging from student laptops to research servers, Snort provides thousands of devices connect daily, ranging from student laptops to servers, and where Snort provides real-time traffic analysis, detecting malicious activities such as malware infections, brute force attacks, and unauthorized access attempts by leveraging signature-based detection. Snort identifies known attacks patterns such as SQL injection attempts in student portal, while its protocol analysis capabilities help uncover anomalies like unusual ports or scans and data exfiltration. Universities often deploy Snort at network choke points such as perimeter gateway data center entrances to monitor both inbound and outbound traffic, ensuring compliance with security policies and regulatory requirements like FERPA or GDPR. Now let's look into that. The NetWitness was an example. NetWitness is a comprehensive threat detection and response platform widely used in university networks to monitor, analyze, and mitigate sophisticated cyber threats in an academic setting where diverse systems such as research databases, student portals, and IoT enabled campus infrastructure are prime targets for attackers. NetWitness provides end to end visibility by integrating and aggregating and correlating data from logs, network traffic, and endpoints. Its advanced behavior analytics and machine learning capabilities help detect anomalies like unauthorized access attempts, data exfiltration, or ransomware activity. For example, if a hacker exploits a vulnerability in a university's learning management system, NetWitness can trace the attack chain across multiple layers, from initial network intrusion or lateral movement, enabling faster containment. Universities both benefit from NetWitness's automated threat intelligence integration, which cross references global threat feeds and local network activity to identify known malicious IPs, domains, or malware signatures. The platform's forensic tools also allow IT teams to reconstruct security incidents such as phishing campaigns targeting faculty or students, credential theft, providing actionable evidence or remediation. Additionally, NetWitness supports compliance reporting for regulations like FERPA or HIPAA, ensuring sensitive data remains protected by combining real-time monitoring with deep forensic analysis. NetWitness helps universities maintain a robust security posture while preparing the next generation of cybersecurity professionals through hands-on training in enterprise-grade threat detection. Using log files as evidence. Let's look into this with an example. Log file serves as critical forensic evidence in university setting. Example that we are running in this lecture, providing an auditable trail of the system activities, network traffic, and user behaviors in cybersecurity incidents such as data breaches, unauthorized access to research databases, or distributed denial of service or DDoS. attacks targeting campus networks, logs from firewalls, servers, and application document timestamps, IP addresses, and action taken. For example, authentication log can reveal brute force login attempts on student portals, while web servers logs may expose SQL injection attacks attempting to steal sensitive information. These records not only help identify the source and scope of an incident, but also support legal and disciplinary proceedings, such as cases involving academic misconduct or policy violations. Universities must ensure logs are securely stored, tamper proof, and retained in compliance with data protection laws like GDPR, FERPA, to maintain their integrity as admissible evidence. To strengthen their evidentiary value, university implement centralized log management systems or SIEM platforms like Splunk or Graylog to aggregate, correlate, and analyze logs across diverse systems. Techniques like hashing and digital signatures preserve logs integrity, while chain of custody documentation ensures forensic admissibility in court. Logs also play a preventive role. Regular reviews of proxy logs, for instance, can detect early signs of insider threats such as unauthorized data transfer by employees, and academic research logs may even validate experimental results or defend against accusations by intellectual property theft by treating logs as both a security tool and legal asset. Universities can enhance accountability, support incident response, and foster the culture of transparency. The types of logs look like authentication, application, operating system event, network devices, security event, and the list can go on. Let's look into this with an example. There are many types of logs. Let's look into a few which are not mentioned on this screen. System logs. System logs record operating system events such as startups, shutdowns, service failures, and kernel errors. In a university system example that we are running in this lecture, these logs help IT teams diagnose hardware failures, crashes in research lab computers, or unauthorized changes to system configurations. For example, repeated login failures in a Linux server log may indicate a brute force attack on our departmental database. Application logs track events within software programs, including errors, user actions, and transactions. Universities rely on these logs to troubleshoot issues in learning management systems such as Canvas, Moodle, or Blackboard. Student portals are or library databases. A sudden spike in error messages from an exam portal could reveal a coding flaw or an attempted exploit, whereas security logs document authentication attempts, firewall activity, and intrusion alerts. These logs are vital for detecting breaches such as unauthorized access to faculty emails or malware infections in campus networks. Failed login attempts from unusual geographic locations might signal a credential stuffing attack. Network logs capture traffic data, including IP addresses, packet flows, and device connections. Universities use them to investigate bandwidth abuse, or such as torrenting in dorms, or cyber attacks like DDoS incidents. NetFlow logs can trace an attacker's path through the network. Database logs record queries, modifications, and access to sensitive data, student records, or research datasets. They help identify SQL injection attacks or insider threats, such as staff member exporting confidential information without authorization. Web server logs track HTTP requests, visitor IPs, and accessed resources. Universities analyze them to detect web based attacks such as defacement attempts or optimized performance. Unusual requests to an admin page may indicate a directory traversal attack. Proxy logs monitor internet usage, including visited websites and downloaded files. They enforce acceptable use policies, blocking malicious sites or tracking data exfiltration. A student repeatedly accessing banned content could trigger disciplinary review. DNS logs resolve domain names to IP addresses or can reveal malicious activity such as phishing campaigns or connections to command and control servers. Certain queries to suspicious domains may indicate malware infections. Authentication logs track login attempts, successes, and failures across systems. Universities use them to spot account takeovers or shared credential abuse. Multiple failed logins to a professor's account could suggest a targeted attack. Cloud logs track activity in platforms like Microsoft 365 or AWS, including file accesses and API calls. They help universities secure hybrid environments such as unauthorized SharePoint downloads or rogue virtual machines in research clouds. IoT devices logs record data for smart campus devices such as HVAC systems or lab sensors. Anomalies like unexpected firmware updates may signal a compromise in a connected building management system. Virtual private network logs or VPN logs track remote connections to university networks, including user IDs and session duration. They help detect compromised accounts, such as students' VPN credentials being used from a foreign country. Email logs monitor sent, received messages, spam filtering, and phishing attempts. A surge in a flagged emails might reveal a campus-wide phishing campaigns targeting student financial data. Endpoint logs from laptops and mobile devices record software changes, USB changes, or malware alerts. IT teams use them to investigate infections, like ransomware spreading through a computer lab. Wireless or Wi Fi logs track device connections to campus networks, including MAC addresses and session times. They help identify rogue access points or devices engaged in malicious scanning. Compliance audit logs. Audit logs provide a tamper proof record of policy enforced actions, file access or privileges changes. They prove due diligence during regulatory audits, HIPAA for health research data. The printer logs track document prints, user IDs, and timestamps. In universities, they deter misuses such as unauthorized printing of copyrighted material to excessive personal use. Virtualization logs monitor hypervisor activity and VM operations. IT staff use them to detect resource abuse in cloud labs on unauthorized VM deployments by students. Industrial control systems or ICS logs track critical infrastructure like power grids or campus facilities. Unusual commands in these logs could indicate a threat to physical safety systems. Last not the least, social media logs for universities managing official accounts. These logs track posts, login or detection, and detection as well. They help identify hacked accounts, spreading misinformation or fraudulent scholarship offers. Wireless, the IEEE specification 802.11a is a description, comes first widely used as Wi-Fi standard operates at 5 gigahertz. 802.11b at 2.54 gigahertz. Indoor range is 125 feet. Bandwidth is 11 Mbps. 802.11g backward compatibility with 802.11b. Indoor range is 125 feet. Bandwidth is 54 Mbps. 802.11n operates at 2.4 or 5.0 gigahertz. Indoor range is 230 feet. Bandwidth is 100 and 140 Mbps. I suggest you to look into these carefully so you understand how this works. I leave it to your discretion and read. You can pause the lecture here and look at this. Wired equivalent privacy, or WEP, uses the stream cipher RC4 and to secure the data, and a CRC32 checksum for error checking, and the list goes on. Wi-Fi Protect Access, WPA, uses Temporal Key Integrity Protocol, TKIP, 128-bit per packet key that dynamically generates a new key for each packet. Other wireless protocols are ANT+, ZigBee, Z-Wave, Bluetooth, and you can read that by pausing the slide here. Forensic concerns with wireless networks. Data perpetrator uses a wireless network entry point for a direct network attack or theft of data. Did any attacker use a third-party wireless network, such as a hotel hotspot, or conceal his or her identity? Wireless storage devices. I suggest you to look into these and learn more. This will allow you to understand how the storage is significant in any given devices within a university system, as we are looking into that example as a running example. Wireless network discovery tools, the NetStumbler, MaxTumbler, and iStumbler. I suggest you look into that using Google Scholar, that how people have used in terms of research and the applications of these tools. Router forensics is a router is a hardware or software device that forwards data packets across a network to a destination network. I suggest you look into this in more detail in your studies. Router basics. It has a network card, it has a hub, it is a switch and a router. I suggest you look into this and see how people have used at Google Scholar or IEEE Explore in terms of conducting their research on routers and the network traffic. Types of router attacks. Router table poisoning. Incorrect router table entries can result in artificial congestion, the router becoming overwhelmed, and attacker being allowed access to data in the compromised network. Getting evidence from the router. Do not shut down the router. Can erase valuable evidence. Do not alter anything. Document your process. Connect with the router to run certain commands. Here are some router commands given. Firewall forensics, packet filter, and stateful packet inspection. I suggest you look into these at IEEE Explore or Google Scholar to learn how people have worked on firewall forensics. Collecting data. All the traffic going through a firewall is part of connection. A connection consists of two IP addresses communicating with each other and two port numbers that identify the protocol or the service. Attempts on same set of ports from many different internet sources are usually due to decoy scans. Carefully check firewall logs for any sort of connections or attempted connections on those ports. Use protocol analysis to determine who attacker is. Summary of this lecture is we looked at network packet structure, network packet capture, network packet analysis, router forensics, and firewall log and forensics. So hope this has given you something to understand in more depth in computer forensics. See you in the next lecture. Happy learning.